There is something buried inside a dataset from Mars that nobody has fully explained, and the more you dig into it, the stranger it gets. In 2021, NASA's Curiosity rover was sitting quietly on the floor of Gale Crater, doing what it always does, sniffing the Martian air, sampling the thin atmosphere, and sending that data back to Earth. And buried in one of those measurements was something that stopped scientists cold: a spike. A massive, inexplicable spike in methane that showed up in the data, vanished almost as quickly as it appeared, and has been causing arguments in the scientific community ever since. Now, on the surface, methane might not sound like the most exciting thing in the world. It's a gas. It smells bad. Cows produce a lot of it. But on Mars, methane is one of the most important words in all of planetary science, because methane breaks down. It falls apart under ultraviolet radiation from the sun. It reacts with other chemicals in the atmosphere. It doesn't just sit around for millions of years. Which means that if you find methane on Mars, it had to have been produced recently. Something is making it right now, or at least in the very recent geological past. And that something is either geological or it is biological. Those are essentially the only two options on the table, and we genuinely do not know which one it is. If you have ever been curious about the kind of science that keeps astronomers and astrobiologists up at night, stay with me. Because what the full dataset actually shows is far more complicated, far more interesting, and far more unsettling than any headline you have ever read about Mars methane. And before we go any further, if this is the kind of content you want more of, hit subscribe right now, because we are just getting started. Let's go back to the beginning. Not just 2021, but all the way back to when we first started looking for methane on Mars. Because the 2021 spike didn't come out of nowhere. It was the latest chapter in a story that has been building for decades. The first serious suggestion that Mars might have methane in its atmosphere came in the early 2000s. Astronomers using telescopes on Earth, pointing them at the thin Martian sky, thought they detected traces of the gas. The numbers were small, parts per billion, barely above the noise floor of the instruments they were using. But they were there, or they seemed to be there, and immediately the scientific community split into two camps. One group said, "This is extraordinary, and we need to investigate." The other group said, "These measurements are within the margin of error, and we should not get excited." Both groups were being completely reasonable given what they knew at the time. Then in 2004, the European Space Agency's Mars Express spacecraft arrived in orbit around Mars and started doing its own atmospheric analysis, and it also found methane. Same rough numbers, around 10 parts per billion in certain regions. And crucially, the methane appeared to be concentrated in specific areas rather than evenly distributed across the whole planet. This was significant. If methane was being produced by some kind of global geological process distributed evenly across the planet, you would expect to find it spread out. The fact that it was concentrated suggested point sources, localized spots where something was actively generating the gas. And then things got really interesting when scientists started cross-referencing those methane hotspots with maps of the Martian surface. Some of those concentrations appeared to line up with regions where liquid water had once flowed, or where there was known geological activity, or where the ground had particular chemical compositions. Not definitive, not proof of anything, but suggestive enough that people started talking very seriously about the possibility that something down in the Martian subsurface was generating methane. Enter Curiosity. NASA's Mars Science Laboratory rover landed in Gale Crater in August 2012, and it was the most sophisticated robot ever sent to another planet. It had a suite of instruments specifically designed to analyze the chemical composition of Martian rocks and soil and atmosphere. One of those instruments was called SAM, which stands for Sample Analysis at Mars. SAM could sniff the air and tell you with extraordinary precision exactly what was in it. And when Curiosity first turned SAM on and pointed it at the Martian atmosphere, the initial readings suggested that methane was essentially undetectable, less than 1 part per billion, which created a genuine contradiction with what the orbital and ground-based telescopes had been measuring. And that contradiction set off a scramble in the scientific community. Some researchers said the telescopes were wrong. Others said Curiosity's location at the bottom of Gale Crater might not be representative of the whole planet. Others suggested that maybe the methane was episodic, not constant, appearing in bursts rather than maintaining a steady background level. And this last idea turned out to be the closest to the truth. Because starting around 2013 and 2014, Curiosity started catching occasional whiffs of elevated methane. Not steady background levels, but spikes. Moments where the concentration would jump up dramatically and then drop back down. The most notable of these early detections came at the end of 2013, when SAM recorded a spike that reached around 7 parts per billion. For a planet where the baseline methane is effectively zero, that is an enormous jump. Scientists were cautious, as they should be, but they were also genuinely excited. A study published in Science in 2015 described these early detections and tried to make sense of what was happening. The researchers noted that the spikes seemed to correlate loosely with warmer seasons on Mars, which was interesting because warmer temperatures would be consistent with methane being released from frozen subsurface deposits as the ground warmed up and gas could escape through cracks. This is a process that happens on Earth in permafrost regions, and it's entirely plausible that something similar could be occurring on Mars. But that was one explanation among many, and nobody had enough data to really nail it down. Then came the ESA's ExoMars Trace Gas Orbiter, which arrived at Mars in 2016. And this is where the story takes another unexpected turn. The Trace Gas Orbiter was specifically designed to detect methane and other trace gases in the Martian atmosphere with extraordinary sensitivity. It could detect methane at concentrations of parts per trillion, far more sensitive than anything that had been used before. And when it started taking measurements in 2019, it found essentially no methane at all, zero, or more precisely, less than 0.05 parts per billion, which is below the detection threshold of the instrument. This was a bombshell. Here you had the most sensitive methane detector ever sent to another planet finding nothing, while a rover sitting on the surface was periodically detecting spikes of several parts per billion. How is that even possible? How can something be detected at the surface but not from orbit? That is not how atmospheric gases normally work. If methane is present at the surface, it should diffuse upward and eventually be detectable from orbit. Unless something was destroying it very quickly before it had a chance to rise. Unless the Martian atmosphere had some chemical process that was eating up the methane almost as fast as it was being produced. Or unless one of the instruments was wrong. This discrepancy became one of the central mysteries in Mars science. Papers were published examining the wind patterns in Gale Crater, the way air circulates at night versus during the day, whether local geological features could concentrate or trap methane near the surface. Some researchers proposed that there might be a chemical process in the Martian soil itself that was rapidly oxidizing the methane before it could reach orbital altitudes. Others proposed that Curiosity's SAM instrument might have a contamination issue, that some organic material inside the rover itself might be generating false positives. This is not a reckless accusation. It is exactly the kind of thing you have to consider when doing science at this level of precision. You have to be your own harshest critic. Now, all of this context matters enormously when you start trying to understand what happened in 2021. Because by that point, Curiosity had been on Mars for 9 years, SAM had taken thousands of atmospheric measurements, and the scientific community had been arguing about Martian methane for the better part of 2 decades. The 2021 spike didn't land in a vacuum. It landed in the middle of an already complicated and contested scientific landscape. So what exactly happened in 2021? Let's get into the actual data, because this is where it gets really fascinating. Curiosity had by this point established a fairly consistent pattern of atmospheric sampling. SAM would regularly pull in small amounts of Martian air and analyze them with a device called a tunable laser spectrometer, which is essentially an instrument that shines lasers through gas and measures how the light is absorbed. Different molecules absorb light at different frequencies, so you can figure out what you're looking at with remarkable precision. The instrument had been doing this for years, and researchers had gotten very good at interpreting its outputs, understanding its quirks and its error bars. What the data from 2021 showed was a methane detection that was substantially higher than anything Curiosity had recorded in the preceding years. The specific numbers have been subject to some scientific debate about how to properly calibrate and interpret them, which we will get into, but in broad terms, the concentration was well above the baseline and well above previous spikes. This was not a marginal detection teetering on the edge of statistical significance. This was a clear, sharp signal that stood out from the surrounding measurements. And then, relatively quickly, it was gone. Subsequent measurements showed the methane concentration dropping back down toward the baseline. The spike appeared and disappeared within a relatively short window of time. This rapid appearance and disappearance is actually one of the most scientifically important features of the whole event, because it tells you something about the source. A spike that appears quickly and disappears quickly suggests either a nearby, localized source that turned on and then turned off, or a process that produces methane in pulses rather than continuously. Let me give you a sense of what some of the proposed explanations look like, because this is where things branch out into multiple directions simultaneously, and understanding all of them is important. The geological explanation for Mars methane generally involves a process called serpentinization. This is a chemical reaction where water interacts with certain types of iron and magnesium-rich rocks called ultramafic rocks, and as a byproduct of that reaction, you get hydrogen and sometimes methane. This process happens on Earth all the time. There are places on the ocean floor where serpentinization is ongoing, and the methane produced there supports entire ecosystems of microorganisms. On Mars, there is strong geological evidence that the right kinds of rocks exist, that water was once abundant, and that the conditions for serpentinization existed in the past and potentially still exist in the subsurface today, where temperatures and pressures could allow liquid water to persist. Under this model, what would cause a spike at the surface is some kind of release mechanism. You could imagine methane that has been accumulating in pockets underground, suddenly finding a pathway to the surface through a crack or fracture that opened up, perhaps due to a Marsquake or a thermal expansion event. You release a burst of gas, it briefly spikes at the surface, and then it disperses or gets chemically destroyed. This is a completely plausible mechanism. It requires no life at all. It just requires geology. But then there is the biological explanation, and this is the one that makes everyone's pulse quicken a little bit, even the most skeptical scientists, because they are scientists and they understand exactly what it would mean. On Earth, a significant portion of the methane in our atmosphere is produced by microorganisms called methanogens. These are ancient organisms, archaea rather than bacteria, that live in oxygen-free environments and produce methane as a metabolic byproduct. They are found in swamps, in the guts of ruminants, in deep subsurface rock formations, in hot springs, in the ocean sediments. They are extraordinarily hardy organisms that can survive in conditions that would kill most other forms of life. And crucially, they can survive underground, using chemical energy rather than sunlight, which means sunlight is not a requirement for their existence. If Mars has a subsurface liquid water environment, which is increasingly supported by radar data from orbiters suggesting liquid water may exist beneath the southern polar ice cap, then the conditions for methanogens to survive are not obviously impossible. The temperature would be right in some zones. The chemical feedstocks they need could be present. The absence of oxygen, which methanogens actually prefer, is not a problem on Mars. It is a feature. A methane spike from a biological source would look exactly like a methane spike from a geological source. You cannot tell them apart from the measurement alone. You would need additional chemical signatures or direct sampling to know which one you are dealing with. Now, there is a third category of explanation that deserves serious attention, even though it is less exciting. Instrument artifact and calibration uncertainty. Science does not work the way movies portray it, where you get a reading and you immediately know what it means. Real scientific instruments have quirks. They have systematic errors. They have calibration drift. Over 9 years on the Martian surface, Sam had experienced exactly the kind of slow changes in behavior that any complex instrument experiences in a harsh environment. The team responsible for Sam was constantly updating their calibration models, accounting for changes in instrument behavior, and trying to separate real signals from instrumental noise. A 2022 analysis of the Curiosity methane data took a very detailed look at some of the 2021 measurements and raised concerns about whether certain aspects of the calibration were fully accounting for instrumental effects. This is not an accusation of sloppiness. It is exactly the kind of rigorous self-examination that good science requires. The question was whether the spike was real, a genuine increase in atmospheric methane concentration, or whether it was partly or wholly an artifact of how the instrument was behaving in certain conditions. One specific issue that has come up repeatedly in discussions of Curiosity's methane data is the timing of measurements. SAM makes measurements at different times of day, and it turns out that the Martian atmosphere does interesting things with methane at different times. Some analyses of the data have suggested that methane concentrations measured at night tend to be higher than those measured during the day, which is the opposite of what you would expect if sunlight-driven chemistry were destroying the methane. The nighttime enhancement has been proposed as evidence for a process by which methane seeping up from the ground gets trapped near the surface in calm nighttime air conditions, then gets mixed up and diluted when daytime heating creates convective air currents. The 2021 spike needs to be understood in the context of this day-night cycle. If some of the elevated readings were taken during conditions where methane concentrates near the surface anyway, then the spike might be partly a timing effect on top of a genuine but smaller increase in absolute methane abundance. This is the kind of nuance that gets lost completely in the headlines. The reality is several overlapping effects happening simultaneously, and separating them requires careful modeling of Martian atmospheric dynamics and very precise calibration work. Let me talk about what the full dataset, not just the 2021 spike in isolation, actually shows when you look at it as a whole. Curiosity's years of atmospheric measurements have revealed a picture of Martian methane that is variable, episodic, and locationally dependent. The baseline methane concentration in Gale Crater appears to be very low, consistent with essentially zero, for long stretches of time. Then there are periods when something changes and the concentration rises. These elevations have been correlated in some analyses with seasonal patterns. Mars has seasons, just like Earth, because it has an axial tilt, and it also has a fairly eccentric orbit that means it gets significantly closer to the Sun at some points in its year than others. These orbital variations affect surface temperatures, and surface temperature affects how gases are exchanged between the ground and the atmosphere. One of the more intriguing patterns that has emerged from the full dataset is that some of the higher methane readings seem to cluster during the warmer southern summer on Mars, which is also when Mars is closer to the Sun and the southern hemisphere experiences its highest temperatures. This is exactly what you would expect if methane were being released from subsurface reservoirs as the ground warms and allows gases to migrate more easily through the soil. The correlation is not perfect, and not every analysis agrees on its strength, but it is consistent enough that researchers take it seriously. There is also a geographic dimension to this that the full dataset is just beginning to hint at. Gale Crater sits in a specific location on Mars, at the boundary between the southern ancient highlands and the lower northern plains. The floor of the crater is a complicated geological environment with a central mountain of layered sedimentary rock, ancient lake deposits, and various rock types that have been altered by water and chemical processes over billions of years. Some researchers have proposed that Gale Crater might be an unusual location for methane in ways that are specific to its geology, which would complicate efforts to generalize the Curiosity measurements to the whole planet. And this brings us back to the contradiction with the trace gas orbiter data. How do you reconcile a rover on the surface occasionally detecting spikes of several parts per billion with an orbital instrument designed specifically to find methane detecting essentially nothing? Several reconciliation attempts have been proposed, and none of them is completely satisfying. One is the destruction hypothesis. If the Martian atmosphere or surface contains some highly reactive oxidizing agent that destroys methane very rapidly, methane could be produced at the surface, detected locally before it spreads, and then destroyed before it reaches orbital altitudes. Some research has pointed to hydrogen peroxide and perchlorate compounds in the Martian soil as potential oxidizers that might accomplish this. These compounds are known to exist on Mars. They were detected by the Viking landers back in the 1970s, and they are chemically reactive enough to potentially explain rapid methane destruction. But the math is tricky. You would need the destruction to happen fast enough to prevent any methane from reaching orbital altitudes, and the numbers do not always work out comfortably. Another reconciliation attempt is the temporal mismatch hypothesis. The trace gas orbiter and Curiosity were not always measuring the atmosphere at the same time. The rover takes sporadic measurements. The orbiter has its own measurement schedule. If methane production on Mars is genuinely episodic, then it is at least theoretically possible that the orbiter just happened to not be looking at the right time or the right place when methane was being produced. This is a less satisfying explanation because the orbiter takes a lot of measurements, but it cannot be completely ruled out. A third possibility is the spatial mismatch hypothesis. Gale crater might be unusual. Maybe methane production in that specific location, from that specific geology, happens to be above average for Mars as a whole, and the orbital measurements represent the planet-wide average, which is genuinely close to zero, while the local crater environment produces occasional bursts. In this case, both instruments would be correct. They would just be measuring different things. There was also a genuinely interesting 2020 study that tried to use computer models of Martian atmospheric circulation to figure out whether methane produced at the surface of Mars could stay confined near the surface for long periods. The modeling suggested that under certain nighttime conditions in Gale crater, with low wind speeds and stable air layers near the ground, methane could indeed accumulate near the surface without efficiently mixing upward into the broader atmosphere. This would mean that a rover sitting at the crater floor could detect elevated concentrations that an orbiter, literally kilometers above, would never see. If this model is correct, it suggests that the instruments are not in contradiction, they are just sampling fundamentally different atmospheric volumes. But here is the thing, and this is the part that I think deserves to be said very clearly. All of these reconciliation attempts are hypotheses. They are reasonable, well-motivated scientific hypotheses supported by various lines of evidence, but none of them has been definitively proven. The Mars methane mystery is not solved. The 2021 spike is not explained. We have a list of plausible mechanisms, and we cannot yet point to one and say, that is it, that is the answer. And that is actually one of the most important things about science. The discomfort of genuine uncertainty is not a failure of the scientific process. It is the scientific process working correctly. The wrong move would be to pick the most convenient explanation and declare victory. The right move is to keep measuring, keep questioning, and keep being honest about what you do not know. So what happens next? What is the plan for actually resolving this mystery? Several things are in motion simultaneously. Curiosity is still operating, still taking atmospheric measurements, and the team continues to refine their calibration and analysis methods. Every additional measurement adds to a database that is now over a decade long, and longer datasets reveal patterns that shorter ones hide. The team published updated analyses in recent years that tried to fully account for instrumental effects, atmospheric dynamics, and seasonal variations, and the picture that emerges is still one where genuine episodic methane elevations cannot be fully explained away. Something real appears to be happening. The debate is about exactly how large it is, how often it occurs, and what is causing it. The Trace Gas Orbiter continues to operate and refine its measurements. Its sensitivity has been improving as the team gets better at operating the instrument and removing sources of systematic error. There have been reports of tantalizing hints in the TGO data, very faint signals that might be consistent with very small methane concentrations, but the team has been appropriately cautious about claiming a detection. If TGO eventually does confirm even a tiny amount of methane in the broader Martian atmosphere, that would be an enormous step toward reconciling the contradiction with curiosity and would put the mystery on a much firmer footing. The Perseverance rover, which landed in Jezero crater in 2021, has its own suite of atmospheric instruments and has been contributing additional data points about methane from a completely different location on Mars. Jezero is a former lake system on the other side of the planet from Gale crater, and comparing atmospheric measurements from two different locations simultaneously is scientifically invaluable. If methane spikes appear at one location but not the other, that tells you something about the geographic distribution of the sources. If they appear at both locations at roughly the same time, that tells you something different. Having two rovers doing this simultaneously is exactly the kind of comparative science that can start to break the mystery open. There are also proposed future missions that could address this question much more directly. A Mars sample return mission, which has been in development and is the subject of significant debate about cost and timeline, would bring Martian rocks and soil back to Earth, where they could be analyzed in laboratories with equipment far more powerful than anything a rover can carry. If there are chemical biosignatures in Martian samples, the laboratories on Earth would have the best chance of finding them. The isotopic composition of methane is particularly interesting. Life tends to preferentially use certain isotopes of carbon over others, so methane of biological origin has a distinctive isotopic signature compared to methane of geological origin. Measuring that signature with high precision could potentially tell you definitively which kind of methane you are dealing with. But to do that analysis properly, you really want to bring a sample home. There are also concepts being studied for a dedicated methane source mapper, a mission that would orbit Mars at low altitude and use extremely sensitive infrared spectrometers to pinpoint exactly where on the planet methane is being produced, if it is being produced. Knowing the geographic location of methane sources with precision would be transformative. You could then correlate those locations with specific geological features, with known water ice deposits, with regions that radar data suggests might have subsurface liquid water, and start building a much more complete picture of what is actually going on. But let us take a step back from the technology and the missions and the calibration debates for a moment and think about what is really at stake here. Why does any of this matter? Why should you care about a trace gas on a cold, dead-looking planet? Because the question of methane on Mars is ultimately a question about whether we are alone. I want to be very careful about how I phrase that, because science requires precision. The detection of methane on Mars does not prove life. It does not even strongly imply life. Geology can produce methane without any biology whatsoever, and even if the methane is biologically produced, that biology might be microbial and completely unrelated to anything we would recognize as complex life. We are not talking about little green men. We are talking about microorganisms, single-celled organisms far simpler than even the bacteria you can see with a basic microscope. But here is why it still matters more than almost anything else in science. If life arose independently on Mars, even if that life is just a simple methanogen living in some deep subsurface crack where liquid water occasionally exists, that discovery would fundamentally transform our understanding of the universe, because it would tell us that life is not a cosmic accident that happened once on one lucky planet. It would tell us that life emerges wherever the conditions are even remotely right, and if that is true for Mars and Earth in the same solar system, then the galaxy, which contains hundreds of billions of stars, many of them with planets, becomes a place that is absolutely teeming with life. The implications are staggering. Philosophically, scientifically, culturally, religiously, there is no area of human thought that would not be touched by that discovery. This is why serious, rigorous scientists spend their careers arguing about parts per billion of a trace gas on a distant planet. They understand the stakes. They understand that being wrong in either direction has enormous consequences. If you claim life when it is actually geology, you have misled humanity and wasted resources. If you dismiss a real biosignature because it is inconvenient or because the instrument calibration is uncertain, you might have missed the most important discovery in human history. Both errors are catastrophic, so the caution, the endless debate, the refusal to draw premature conclusions, this is not timidity. It is the weight of understanding what you are actually looking for. There is a concept in science called the prior probability, which basically means, before you see any evidence, how likely did you think something was? For most of the history of planetary science, the prior probability for life on Mars was very low. Mars looked dead. It had no magnetic field to protect it from solar radiation. Its atmosphere was thin and could not hold much warmth. Its surface was covered in perchlorates that would be toxic to most forms of Earth life. The water was gone, locked up in ice, or escaped into space billions of years ago. But that picture has been getting steadily more complicated over the past 2 decades, and the prior probability for subsurface Martian life has been quietly rising as each new piece of evidence comes in. Evidence for ancient rivers and lakes, evidence that Mars had liquid water on its surface for hundreds of millions to potentially billions of years, time enough for life to have gotten started. Evidence for ongoing geological activity that could provide energy sources. evidence for complex organic chemistry in the rocks of Gale Crater, found by Curiosity itself, showing that the chemical building blocks of life were present, evidence that liquid water may still exist beneath the polar ice cap, and now, persistent, repeated, inexplicable spikes of methane. No single piece of evidence is a smoking gun, but taken together, they tell a story of a planet that is not quite as dead as it looks. A planet with a complicated chemical interior, potentially with liquid water in the right places, potentially with ongoing geological processes that could support chemistry, and a planet with methane in its atmosphere that has no fully satisfying explanation. Let me walk you through what we know, very precisely, about what the 2021 data actually shows when you look at the full picture. The measurements in question were taken by SAM's tunable laser spectrometer in enrichment mode, which is the highest sensitivity mode where the instrument processes more air to give a stronger signal. In this mode, SAM has detected methane at concentrations well above the detection threshold multiple times over the mission, with the 2021 measurements representing some of the highest concentrations recorded. The signal was clearly above the instrument noise floor. It was above the systematic uncertainty in the calibration. It was not a case of squinting at the noise and seeing what you want to see. It was a real signal. The measurement was reproduced across multiple independent samples. SAM did not just measure it once. It measured it multiple times in the same period and got consistent results. This matters because a one-time anomaly could easily be a glitch. Multiple consistent measurements of the same elevated concentration are much harder to dismiss. The concentration dropped in subsequent measurements, suggesting that either the source turned off, or the methane was dispersed or destroyed, or the rover moved to a location with a different local methane environment. The transient nature of the spike is one of its most important and most puzzling features. Temperature correlations within the data are complex. The measurements at the time of the spike were not taken under extreme temperature conditions that would be obvious outliers in the instrumental behavior. The team analyzed whether known instrumental effects could explain the readings and concluded that while instrumental effects need to be accounted for, they do not fully explain away the observed concentration. There is an ongoing effort to develop better physical and chemical models of how SAM actually behaves in the Martian environment, because the instrument was designed and calibrated on Earth and then spent years operating in conditions it was never tested in. Improving those models is part of how the community works toward firmer conclusions about what the data really means. One important piece of context that often gets left out of discussions of the 2021 data is that it did not occur in isolation from other Mars methane events. Looking at the full Curiosity dataset, there is a pattern of elevated methane detections occurring at intervals, not on a perfectly regular schedule, but not randomly either. Some researchers have tried to fit these occurrences to models of seasonal gas release from subsurface reservoirs and found that the timing is at least roughly consistent. Others have pointed out that the pattern could also be consistent with episodic geological events like Marsquakes releasing trapped gas. The pattern itself is a data point, but it is a noisy one that can be fit to multiple models. Something else that the full dataset shows, which is worth highlighting, is that between the spikes, the baseline methane in Gale Crater appears to be genuinely very low. This is not a situation where there is a constant elevated methane level with occasional additional spikes on top. The spikes appear on top of what looks like near-zero background concentrations. This episodic pattern is actually harder to explain with a simple, steady-state geological process. A process that runs continuously would produce a continuous low-level background, a process that turns on and off, or a process that accumulates product over time and releases it in pulses would produce exactly the pattern that is being observed. This is actually one of the more compelling aspects of the biological explanation, not because biology is more likely than geology, but because biology naturally produces episodic, pulsed outputs in response to environmental conditions. Methanogens on Earth vary their activity dramatically with temperature, nutrient availability, and other factors. A community of methanogens that was active during warmer seasons and dormant during colder ones would naturally produce the kind of episodic methane spikes that Curiosity has observed. Again, this is not evidence. It is consistency. But in science, when a hypothesis is consistent with the data, and the null hypothesis is not fully adequate to explain the data, you keep looking. One more dimension of the 2021 measurements that deserves serious attention is what else Sam detected at the same time. Methane does not exist in isolation. If you are going to do atmospheric chemistry seriously, you want to look at the full spectrum of what is present, not just the one gas you are most excited about. The presence or absence of other gases, and their relative concentrations, can tell you a lot about the source of the methane. For example, if methane is being produced by serpentinization, you would expect to also see elevated hydrogen, because that process produces both. If it is being produced by methanogens, you might expect different ratios of methane to other gases, depending on exactly what metabolic reactions the organisms are running. If it is being produced by some other chemical process, that too might leave specific fingerprints in the broader atmospheric chemistry. The full chemical picture around the time of the 2021 spike has been the subject of ongoing analysis, and without going into technical details that would require a chemistry degree to follow, the short version is that the picture is consistent with multiple possible sources and does not conclusively rule any of them out, which is unsatisfying but honest. I want to spend a moment on the human side of this story, because behind all of the data and the calibration debates and the competing hypotheses, there are real scientists who have devoted their careers to this question and who feel the weight of it very personally. The Curiosity Science Team is a remarkable group of people who have been working with this rover for over a decade. They have seen Mars through the rover's cameras. They have held Martian rock samples in their data streams. They have argued about numbers deep into the night, across time zones and continents. The methane question has been a source of genuine tension within that community because scientists are human and they disagree, and they care deeply about getting it right, and they know that the stakes of being wrong are enormous. There are researchers in that community who look at the methane data and feel genuine excitement, who lie awake thinking about the possibility that the signal is real and biological and what that would mean. And there are others who are deeply skeptical, who worry about instrument artifacts and calibration errors and the history of false positives in the search for Martian life, and who think the right posture is extreme caution. Both groups are right to feel the way they do. Both impulses, excitement and skepticism, are necessary for science to work properly. The tension between them is not a problem. It is the engine that drives rigor. The history of the search for Martian life is a history of hope and disappointment in roughly equal measure, and the scientists who work in this field know it better than anyone. They know about the famous ALH 84001 meteorite, a rock from Mars that landed in Antarctica and was found in 1984. In 1996, a team of NASA scientists announced that they had found evidence of microbial fossils inside it. The announcement was made at a press conference. The President of the United States gave a speech about it, and the world held its breath. And then, over the following years, alternative explanations for every claimed biosignature were found. The structures that looked like fossil bacteria turned out to be explainable by non-biological chemistry. The case for life in ALH 84001 was not exactly disproved, it was just never proved, and the scientific community gradually lost confidence in it. The people working on Curiosity's methane data know this story. They were in some cases involved in it. They know what it feels like to have a potentially life-indicating signal that turns out to have a boring explanation, and they know what it would feel like to dismiss something real. This history creates a kind of disciplined humility that is the best thing science has going for it. What is also worth noting is that the methane question has become part of a broader revolution in how we think about the habitability of Mars. When the Viking landers touched down in 1976 and failed to find clear signs of life, there was a widespread conclusion in the scientific community that Mars was dead, that the question was settled, that life simply was not there. That conclusion was premature, and the past 20 years of Mars exploration have demonstrated that very clearly. We now know that Mars had liquid water on its surface for at least hundreds of millions of years, and possibly over 1 billion years during its early history. We know that the ancient climate of Mars was warmer and wetter than today. We know that complex organic molecules exist in the Martian rocks, the same kinds of molecules that are the building blocks of life on Earth. We know that some forms of life on Earth can survive in conditions as harsh as anything Mars currently offers, including extreme cold, high radiation, acidic environments, and perchlorate-rich soils. We know that the subsurface of Mars, shielded from radiation and potentially harboring liquid water, is a fundamentally different environment from the barren surface that the Viking landers sampled. All of this means that the question of life on Mars is genuinely open in a way that was not believed to be the case 40 years ago. The methane mystery is one thread in this larger tapestry. It is not the whole story, but it might be one of the most important threads, because methane is something that life produces right now, not millions of years ago but in the present, and detecting it means you are potentially detecting an active process, not a fossil of past life, but living chemistry happening today. There is one more thing I want to touch on before we bring this together, and it is something that rarely makes it into the popular coverage of Mars methane: the implications for our understanding of other worlds. Because what we learn about Mars methane is not just about Mars. One of the most exciting developments in astronomy over the past decade has been the detection of methane in the atmospheres of exoplanets, planets orbiting other stars. The James Webb Space Telescope has already detected methane in the atmosphere of an exoplanet called K2-18b, which orbits a red dwarf star in what is called the habitable zone. Now, K2-18b is very different from Earth. It is much larger and likely has a very deep hydrogen-rich atmosphere, but the detection of methane there was still significant because methane is one of the gases in our list of potential biosignatures for other worlds. The problem with using methane as a biosignature for exoplanets is exactly the problem we are running into with Mars. How do you know if it is biological or geological? If we can figure out the answer to that question for Mars, where we can actually send rovers and get detailed measurements, we get better at answering it for planets we can never visit. The Mars methane mystery is in some sense a training ground for developing the analytical framework we will need when we start seriously looking for life on worlds orbiting other stars. The specific chemistry, the atmospheric dynamics, the instrument calibration challenges, the way you think about false positives and false negatives in biosignature detection, everything we are learning from the Curiosity data is making us smarter about how to search for life elsewhere. Even if the Mars methane turns out to be entirely geological, the scientific work done to figure that out will be invaluable for the search beyond our solar system. So where does all of this leave us? We have a rover that has now been on Mars for over a decade, detecting repeated episodic spikes of methane that have no completely satisfying explanation. We have an orbital instrument that was specifically designed to find methane, finding essentially none, creating a contradiction that multiple hypotheses have attempted to explain and none has fully resolved. We have a dataset from 2021 that represents some of the highest methane concentrations Curiosity has ever measured, sitting in the context of a long record of similar but smaller events, suggesting a pattern of episodic methane production rather than a one-time event. We have three broad categories of explanation: geological processes like serpentinization, biological processes like methanogenesis, and instrumental effects, and we cannot definitively rule any of them out. We have a scientific community that is working hard, arguing productively, and being appropriately careful about not overclaiming in either direction. And we have a series of future missions and analytical improvements that offer real hope of making progress on this question over the next decade. What the full dataset actually shows is not a solved mystery. It shows a persistent, recurring, genuinely puzzling phenomenon on another planet that may be geological and may be biological, and whose resolution will require more data, better instruments, and possibly samples brought back to Earth. It shows a planet that is not simply dead and simple, but is chemically active and complicated in ways we are still working to understand. And it shows something else, too. It shows the scientific process in action at its most difficult and its most important. When the stakes are this high, when the question is literally whether or not we are alone in the universe, there is no room for shortcuts, no room for wishful thinking,